What if the most terrifying object in the universe was also the giver of life? For generations, this question has lived only in the ink of our novels, and the flickering light of our cinema screens a grand and terrible fantasy. We have travelled there in our dreams, standing on the shores of alien worlds, where the sky is dominated not by a sun but by a wound in space-time itself. An abyss of perfect blackness framed by the ghostly swirling fires of captured light. It is a vista of sublime horror, the ultimate cosmic spectacle where a planet circles the drain of reality. We have imagined the strange sunrises where the accretion disk of a supermassive black hole ignites the horizon in a blaze of X-rays and gamma radiation painting the landscape in colours no earthly eye was ever meant to see. We have envisioned the gravitational lullabies of these worlds, where the very fabric of time is stretched and distorted, a day passing for a decade in the universe beyond. These are the crown jewels of our science fiction, the settings for our most epic tales of survival and discovery landscapes, born from a marriage of our deepest fears and our most profound sense of wonder. They represent the theoretical edge, the place where the known laws of physics are pushed to their breaking point. And for nearly a century, that is all they were allowed to be magnificent, impossible fiction. The scientific consensus was not just skeptical, it was absolute. A black hole was a zone of pure annihilation, a cosmic predator of unparalleled ferocity. To speak of a planet in its vicinity was to speak of a snowflake in a blast furnace. The arguments against such a world were as robust as they were terrifying. First, there was the violence of its birth. A stellar mass black hole is the collapsed heart of a giant star forged in the fury of a supernova, an explosion so cataclysmic it can outshine its entire galaxy. Any planets that had been orbiting that star, any celestial neighbours would have been scoured clean their atmospheres, stripped away their surfaces, flash-boiled into molten slag, before being violently ejected into the lonely darkness of interstellar space. They would be cosmic orphans flung far from the gravitational wreckage of their parent star. No world, we believed, could possibly survive such a celestial conflagration. It was an act of sterilising fire from which no ecosystem, no geology, no planetary integrity could ever recover. But even if by some miracle a rogue planet were to wander in from the interstellar void and be captured by the black hole's immense gravity, its fate would be just as grim. It would face a trial by forces that defy comprehension. The most infamous of these is the tidal force, the same gentle power that raises the oceans on Earth, but magnified to a scale of cosmic torture. As a planet draws closer, the gravitational pull on its near side would be exponentially stronger than the pull on its far side. This differential would stretch the world, pulling it apart like taffy. We have a name for this process, a term that is both clinically descriptive and viscerally horrifying: spaghettification. The planet's crust would fracture, its mantle would liquefy and flow, and its core would be drawn out into a stream of superheated matter. The very atoms of the world would be unmade, stretched into a thin glowing noodle of plasma before being consumed by the singularity. It is not a collision. It is a disassembly, a methodical and inescapable deconstruction at the hands of raw gravity. And for any world that somehow managed to find a stable orbit far enough to avoid being stretched into oblivion, another menace lurked: the accretion disk. This is the luminous swirling vortex of gas dust, and the shredded remains of stars that spirals into the black hole. It is a celestial banquet of unimaginable scale and violence. The friction within this disk heats the material to millions of degrees, transforming it into a relentless celestial blowtorch. It shines not with the gentle life-giving light of a star, but with a lethal glare of high-energy radiation. X-rays and gamma rays, the most destructive forces on the electromagnetic spectrum, would flood any orbiting planet. This is not the kind of energy that fosters life. It is the kind that shatters DNA, boils away oceans, and sterilizes a planet's surface down to the bedrock. It is a wall of hard radiation, a permanent system-wide death zone. The incandescent carousel of doom, we reasoned, would make any notion of a stable, habitable planet utterly laughable. To survive here, a world would need a magnetic field of impossible strength, and an atmosphere denser than anything we have ever conceived a planetary fortress, against a constant nuclear-level assault. Furthermore, the gravitational environment itself was thought to be a chaotic minefield. Black holes are not serene, lonely objects. They're often surrounded by the swirling remnants of their formation, other stars or even other black holes in complex binary or trinary systems. The gravitational dynamics would be a dizzying, unpredictable dance. A planet's orbit supposedly stable could be perturbed by a passing star, its trajectory altered just enough to send it on a fatal plunge toward the event horizon, or eject it from the system entirely. In this cosmic mosh pit, the delicate clockwork precision required for a stable planetary orbit seemed a fantasy. There were too many variables, too many agents of chaos. The gravitational harmony that allows a world like Earth to exist peacefully circling its star for billions of years was simply not on the menu. The heart of the galaxy, where the supermassive black holes reside, was seen as a place of violent celestial billiards, not a nursery for planets. The entire concept was relegated to the imagination, a place where the rules of astrophysics could be conveniently bent for the sake of a good story. This was the orthodoxy. It was logical, it was supported by our models, and it painted a clear picture of black holes as cosmic dead ends. They were the graveyards of the universe, not the cradles. And yet the universe has a persistent habit of being far more clever, far more strange, and far more creative than our neat and tidy models predict. Over the past few decades, whispers began to emerge from the fringes of theoretical astrophysics. Quiet questions that chipped away at the monolithic certainty of the old paradigm. We discovered planets in the most unlikely of places, challenging our very definition of what a planetary system should look like. We found worlds, orbiting pulsars, the rapidly spinning corpses of massive stars that sweep the cosmos with beams of intense radiation. If a planet could survive, or perhaps even form in the bizarre aftermath of a supernova that created a pulsar, could the story of a black hole's aftermath be more complex than we had assumed? These pulsar planets were the first clue, the first piece of evidence that the universe forms worlds, in environments we once dismissed as hopelessly barren and violent. The questions grew bolder. What if a planet wasn't a survivor of the star's death, but a child of it? What if long after the supernova's fury had faded and the black hole had settled into its silent reign, a new disk of material could form, not the hellishly hot accretion disk of infalling matter, but a vast, cool, stable protoplanetary disk composed of the leftover gas and dust from the initial explosion. A disk of cosmic debris and captured interstellar material slowly coalescing in the gravitational grip of the black hole far from the immediate danger zone. This was a radical idea. It proposed that a black hole could in a sense mimic a star acting as a gravitational anchor for a new generation of worlds. These would be second generation or even third generation planets, born not from the gentle nursery of a nebula, but from the ashes of a stellar cataclysm. The black hole would not be their destroyer, but their parent. This concept, once a mere thought experiment, began to gain traction. As our computer simulations grew more sophisticated, our models started to show that such a disk could indeed form, that it could be stable for millions, even billions of years, and that within it the familiar processes of planetary formation, the slow gathering of dust into pebbles, pebbles into planetesimals, and planetesimals into full-fledged planets could occur. Suddenly, the seemingly impossible began to look merely difficult. The cinematic vision of a world silhouetted against the swirling light of a black hole began its slow migration from the realm of science fiction to the pages of peer-reviewed scientific journals. We started to give them names like planets, or black hole planets. We calculated their potential orbits, modelled their formation, and debated their composition. The impenetrable wall of scientific orthodoxy began to crumble, not from a single dramatic discovery, but from the steady pressure of 1,000 new calculations, new observations, and a willingness to ask, what if we were wrong? What if the death of a star wasn't the end of the story for that solar system, but merely the end of a chapter? What if it was the prologue to an entirely new and far stranger narrative? This shift in perspective was profound. It reframed the black hole from a pure agent of cosmic destruction into a potential agent of cosmic recycling and creation. It suggested that the universe, in its relentless drive to create complexity, could plant the seeds of new worlds in the most hostile gardens imaginable. And with the possibility of their existence came an even more audacious question. If these planets could form, if they could find stable orbits, could they also harbour life? The problem of energy, once seen as an insurmountable barrier, was now re-examined with fresh eyes. A planet orbiting a black hole would have no star to warm it, but perhaps it wouldn't need one. If the world was orbiting a supermassive black hole with a large stable accretion disk, that disk itself could serve as a distant perpetual sun. From far enough away, its lethal hard radiation would be tamed by distance diffused into a gentle life-sustaining warmth. The light from this sun would be otherworldly, a diffuse glow from a swirling ring of fire occupying a huge portion of the sky, but it would be a source of energy nonetheless. For a planet orbiting a smaller dormant stellar mass black hole with no accretion disk, other possibilities emerged. The cosmic microwave background radiation, the faint afterglow of the Big Bang, is normally incredibly cold. But for a planet orbiting very close to a black hole, the intense gravitational field and the planet's own velocity would blue shift this radiation, dramatically increasing its energy and turning this faint cosmic hum into a source of heat. The cold, empty universe itself could become a blanket of warmth. Even more tantalizing was the prospect of tidal heating. A planet in a slightly elliptical orbit around a black hole would be constantly squeezed and stretched by the fluctuating tidal forces. This constant kneading of the planet's interior would generate immense friction and heat, warming the world from the inside out. We see this very process at work in our own solar system, on moons like Jupiter's Io and Europa, where gravitational flexing creates volcanic activity and maintains liquid water oceans beneath a shell of ice. Around a black hole, these tidal forces would be titanic. A planet could be geologically hyperactive, its core kept perpetually molten, driving volcanism and plate tectonics recycling chemicals, and potentially powering a biosphere entirely independent of a sun. A world could be warm, wet, and alive in the deepest, darkest void, kept alive not by starlight, but by the rhythmic gravitational breath of the black hole itself. The abyss was no longer a synonym for nothingness. It was now a candidate for a planetary engine, a source of enduring power. And so we find ourselves at a remarkable threshold in human history. The line between our most imaginative fiction and the frontiers of astrophysics has become irrevocably blurred. The questions we once asked only in movie theatres and novels are now being debated in the halls of our greatest scientific institutions. The hunt is no longer for proof that such worlds are impossible, but for the first tantalizing signs of their existence. We are learning to look at the darkest places in the cosmos not as voids to be feared, but as regions of incredible potential ripe for discovery. This is a complete inversion of our cosmic perspective. We are being forced to abandon our comfortable sun-centric view of the universe and consider that the conditions for planetary formation and perhaps even for life might exist in gravitational and energetic regimes that would have been unthinkable just one generation ago. The central thesis of our journey is this: the most extreme objects in the universe might be hosts to the most extreme and perhaps the most surprising forms of cosmic creation. Our mission now is to step through that looking glass, to leave the safety of scientific dogma behind, and to explore the physics, the environments, and the sheer mind-bending possibilities of a planet orbiting a black hole. The story is just beginning. What if the most powerful thing in the universe was an absence? Not a star, not a galaxy, but a lack. A profound and perfect emptiness so potent it can swallow light, bend the flow of time, and hold entire star systems in its thrall. This is not a riddle. It is the fundamental paradox that sits at the heart of our cosmos, a concept so alien to our sun-drenched experience that for decades we treated it more like a monster from mythology than a physical reality. We gave it a name whispered with a certain dread: the black hole. It begins its life in an act of unimaginable violence. Imagine a star, a true titan of the heavens, at least 20 times more massive than our own gentle sun. For millions, perhaps billions of years, it is a magnificent engine of creation, a celestial furnace where the crushing pressure of its own gravity forges hydrogen into helium, helium into carbon, and onward up the periodic table, crafting the very elements that will one day give rise to planets, to atmospheres, and perhaps to us. But this cosmic alchemy comes at a terrible price. The star is in a constant state of war with itself. Its nuclear furnace pushes outward with furious energy, a continuous detonation holding the colossal weight of its own atmosphere at bay. Gravity, the silent patient force of the universe, relentlessly pulls inward, seeking to crush everything to a single point. For eons, these two forces are locked in a spectacular delicate balance. Then the fuel begins to run out. The outward push of fusion falters, the delicate truce shatters, and gravity, the ultimate victor in any cosmic contest, finally wins. In less than a second, the star's core collapses upon itself. The implosion is so rapid, so catastrophic, that it triggers a rebound shockwave of incomprehensible power. The star's outer layers are blasted into space in a supernova, an explosion so brilliant it can briefly outshine its entire home galaxy, a final glorious funeral pyre. But what is left behind in the darkness is the true monster. The core, now freed from the outward pressure that sustained it, continues its collapse unchecked and absolute. It shrinks past the point where its atoms can support themselves, past the point where even the fundamental particles of matter can resist. It crushes itself into a point of zero volume, an infinite density, a place where the laws of physics as we understand them simply break down. This is the singularity. Around this impossible point, gravity becomes a force not of attraction but of damnation. It warps the very fabric of space-time into a bottomless well, a cosmic waterfall from which nothing can escape. Imagine you are in a spaceship near this stellar ghost. You fire your engines trying to pull away. Closer in, you would need to travel faster than you thought possible. Closer still, and you would need to exceed the speed of light itself to break free, an absolute impossibility in our universe. The boundary where the escape velocity equals the speed of light is the event horizon. It is not a physical surface you could touch, but a threshold, a point of no return. Cross it, and you have left the observable universe forever. Your future is no longer a direction in the space, but a destination in time, the singularity. For most of human history, this was the complete story of the black hole. It was the ultimate cosmic predator, the universe's final punctuation mark. It was a gravitational tyrant that shredded stars, devoured gas clouds, and warped the space around it into a funhouse mirror of distorted light. The idea of anything living near such a thing, let alone a planet or world, was pure fantasy, the stuff of the most imaginative science fiction. They were seen as zones of absolute annihilation, celestial voids where the story of the cosmos comes to a dead end. Life, we believed, required stability. It required the gentle, predictable, life-giving energy of a star like our sun, a stable anchor in the celestial ocean. Our own solar system became the blueprint, the gold standard for what a home could be. A rocky planet orbiting a single well-behaved star at just the right distance, the so-called Goldilocks zone, where water could exist as a liquid. It was a tidy, comforting, and deeply ingrained picture, and for a long time it was the only picture we had. But while our theories about cosmic monsters were solidifying, another quieter revolution was beginning. It wasn't a search for destroyers, but a hunt for creators, a quest for other worlds. For millennia, the planets of our own solar system were the only ones we knew. They were wanderers in our sky gods and goddesses in our myths. The idea that the countless other stars in the night sky might also have their own planetary families was an ancient dream, but it was one we had no way of proving. Then, in the late 20th century, our technology finally caught up with our ambition. We built telescopes of extraordinary sensitivity capable of detecting the most subtle changes in a star's light from light years away. We were looking for ghosts. Not the gravitational ghosts of dead stars, but the fleeting shadows of planets as they passed in front of their stellar parents, causing a minuscule, almost imperceptible dip in their brightness. We were listening for the faint rhythmic wobble of a star tugged back and forth by the gravitational dance of an unseen companion. At first, the search was met with skepticism and failure. The signals were buried in noise, the technical challenges immense. But in 1995, a discovery was announced that ripped up our tidy blueprint of the universe. Astronomers found a planet orbiting the star 51 Pegasus. But this was no Earth. It was a gas giant, a behemoth half the mass of Jupiter, roasting in an orbit so tight that its year lasted just 4 Earth days. It was a hot Jupiter, a class of world we had never imagined could exist. Our models said a giant like that should only form in the cold, outer reaches of a solar system like our own Jupiter and Saturn. To find one snuggled up against its star with surface temperatures hot enough to melt iron was a profound shock. It meant that planets were not static objects born into a fixed orbit. They could migrate. They could wander through their own solar systems in a chaotic dance of gravitational encounters, settling in places we thought were forbidden. Our neat and tidy blueprint was wrong. The cosmos was messier, more dynamic, and infinitely more interesting than we had ever dared to believe. And that was just the beginning. The floodgates of discovery had been thrown open. As our techniques improved, the cosmic census exploded. We found super-Earths, rocky worlds much larger than our own. We found mini-Neptunes, gaseous planets smaller than anything in our solar system. We found rogue planets cast out from their home systems to wander the cold, interstellar darkness alone for eternity. Each new discovery was a fresh lesson in cosmic humility, a reminder that our own solar system was not the rule, but merely one possible outcome of planetary formation. Then came a discovery that seemed to lift a page directly from science fiction. We found planets orbiting not one but two suns. These were circumbinary worlds, real-life Tatooines. For decades, the complex gravitational ballet of a binary star system was thought to be far too chaotic to permit stable planetary orbits. We imagined any world born there would be quickly flung into one of its parent stars or ejected into the void, yet there they were. Kepler 16b, a cold Saturn-sized world casting two shadows as it gracefully circled its twin suns. Kepler 47c, a gas giant orbiting in the habitable zone of its binary stars where liquid water could potentially exist on the surface of its moons. These discoveries fundamentally rewired our understanding of stability. If a world could find a stable home amidst the gravitational tug-of-war of two stars, if planets could survive being roasted next to their suns, then the definition of a habitable environment was far broader, far more flexible than we had ever conceived. The Goldilocks zone was not a fixed address. It was a fluid concept dependent on a complex interplay of forces we were only just beginning to grasp. We had proven that life's potential cradle could exist in the most extreme and unlikely of places, and this growing catalogue of cosmic weirdness, this gallery of impossible worlds, made real emboldened a few thinkers to ask an even more radical question. A question that brought us full circle back to the monster in the dark. If a planet can orbit two stars, could a planet in theory orbit a black hole? At first, the idea seemed absurd, a contradiction in terms. How could a world exist in a stable relationship with the universe's most unstable, destructive object? The common image of a black hole is that of a cosmic vacuum cleaner indiscriminately sucking in everything around it. But this, like many of our early assumptions, is a subtle misunderstanding of how gravity works. A black hole's gravitational pull is indeed immense, but it is not infinite at a distance. If you were to magically replace our Sun with a black hole of the exact same mass, something remarkable would happen to the orbits of the planets, nothing at all. The Earth, Mars, Jupiter, they would all continue in their precise clockwork paths unaffected. Gravity only cares about mass and distance. From 93 million miles away, the Earth doesn't know if the mass at the centre of the solar system is a star or a black hole. The pull is identical. The danger zone, the region of chaotic destruction, is actually quite close to the event horizon itself. Here, the gravitational forces are so extreme that they create what are known as tidal forces. Imagine an object like a spaceship or a planet approaching the black hole. The side of the object closer to the black hole is pulled with tremendously more force than the side farther away. This differential pull would stretch the object, pulling it apart like taffy in a process graphically known as spaghettification. This is the fate that awaits any matter that strays too close. It is shredded into a stream of superheated atoms before it ever reaches the event horizon. So for a planet to survive, the first and most fundamental requirement is distance. It would need to orbit far outside this deadly tidal zone, in a region of relative gravitational calm, where the black hole behaves just like any other massive object. The mathematics was surprisingly straightforward. Physicists in the late 20th and early 21st centuries, playing with the equations of general relativity, could easily model such a system. They could calculate the parameters for a stable long-term orbit, a safe zone, where a planet could circle its dark master for billions of years without being torn asunder or swallowed whole, the calculations showed it was physically possible. A world could indeed be gravitationally bound to a black hole. The physics did not forbid it. But this theoretical possibility came with a profound and seemingly insurmountable problem. A planet in such an orbit would be a world of eternal, absolute night. Black holes, by their very definition, emit no light of their own. They don't burn with nuclear fire like a star. They are the epitome of cold and darkness. A planet orbiting one would be a frozen, sterile rock, adrift in a lightless, energy-starved abyss. There would be no photosynthesis, no warmth to drive geological activity, no energy source to spark the complex chemistry that we believe is necessary for life. The orbit could be stable, yes, but it would be a dead orbit, a celestial tomb. The physics allowed for a planet, but it seemed to forbid a world. For a time, this is where the story ended. It was a fascinating but ultimately bleak thought experiment. A planet could exist there, but it could never be a home. It was an idea confined to the blackboards of theoretical physicists, a curiosity with no bearing on our search for life in the universe. We had expanded our horizons from a single sun-drenched blueprint to a vast tapestry of strange and wonderful planetary systems. We had learned that nature's imagination consistently dwarfed our own. But this final frontier, the gravitational domain of a black hole, seemed a step too far. The monster was simply too cold, too dark, too final, or so we thought. We had accounted for the gravity of the black hole, for its darkness, for its terrifying power. But we had forgotten about the light it stole from others. We had overlooked the fury of its victims and the extraordinary possibility that the act of destruction itself could become a source of unimaginable creation. The secret to a living world on the edge of oblivion wasn't in avoiding the monster. It was in harnessing its rage. The very notion of a planet born of darkness, a world clinging to the edge of oblivion, seemed for so long to be a fever dream of science fiction. It was a concept so alien, so contrary to our sun-drenched experience of what a solar system should be, that it was relegated to the furthest fringes of theoretical possibility. To find the courage to even ask the question in a serious scientific forum, we had to first witness the universe breaking its own established rules. The first crack in that comfortable certainty appeared not in the silent gravitational well of a black hole, but in the piercing rhythmic shriek of a cosmic phantom, a pulsar. Before we could hunt for planets in the deepest shadows, we first found them in the most violent light. In 1992, astronomers Alexander Vulschan and Dale Frail were studying a celestial body designated PSR B.57+12. This wasn't a star in any conventional sense. It was a stellar corpse, the hyperdense spinning remnant of a massive star that had long ago perished in a supernova explosion. A pulsar is a cosmic lighthouse, a neutron star spinning hundreds of times per second, sweeping beams of intense radiation across the galaxy. From our vantage point on Earth, these beams register as pulses with a regularity so precise they rival our best atomic clocks. For astronomers, a pulsar's pulse is a metronome of the heavens, a signal you could set your watch to for the next million years, and yet the rhythm of PSR B.57+12 was off. The celestial clockwork was flawed. The pulses were arriving just a little too early, then a little too late in a subtle but undeniable pattern of oscillation. Something was tugging on this stellar zombie, pulling it back and forth in a gravitational dance measured in milliseconds. The force was minuscule, a whisper against a hurricane, but the pulsar's precision was so absolute that even this whisper was detected. The implications were staggering, almost heretical. The only thing that could account for such a rhythmic gravitational perturbation, a wobble in the unwobbleable, was the presence of orbiting companions, planets. This discovery was met with profound skepticism, and for good reason. A supernova, the event that creates a pulsar, is one of the most cataclysmic outbursts in the cosmos. It is a star tearing itself apart, releasing more energy in a few seconds than our own sun will in its entire 10 billion year lifetime. Any planets that had orbited the original star would have been scoured by radiation, then engulfed by the star's expanding outer layers, and finally utterly obliterated by the shockwave of the final detonation. They should have been vaporized, their atoms scattered into the void. To suggest that planets could be found here was like searching for pristine sandcastles in the epicenter of a nuclear blast. It simply made no sense. But the data was relentless, the signal irrefutable. As the observations continued, the picture became clearer and even more bizarre. Not one, but at least 2 planets were confirmed, with a third suspected. These were not the gas giants we expected to find in the outer reaches of systems, but small rocky worlds, one about 4 times the mass of Earth, the other about 3. They were true terrestrial planets born in an environment that should have been a sterile wasteland. So where did they come from? The unavoidable conclusion was as creative as it was violent. They were not survivors, they were children of the apocalypse. They were second-generation planets formed not from the primordial gas and dust that built the original star, but from the wreckage of the supernova itself. Imagine the scene after the star's fiery death. A fraction of the ejected material, a disk of heavy elements and cosmic shrapnel, failed to escape the gravitational grip of the newborn pulsar. This debris disk, glowing with residual heat and irradiated by the pulsar's relentless beams, became a new celestial nursery. Over millions of years, in this most unlikely of crucibles, dust and rock began to clump together. Grains became pebbles, pebbles became boulders, and boulders coalesced into planetesimals, eventually accreting into the worlds we see today. They were zombie planets built from the ashes of a dead system circling a stellar ghost. This discovery did more than just add a few new worlds to our celestial catalogue. It fundamentally and forever shattered our provincial ideas of where planets could exist. If a world could be forged in the radioactive fallout of a supernova and survive in the pulsating glare of a neutron star, then the universe was far more resilient and far more imaginative than we had ever dared to believe. It gave us permission to look at the most extreme environments not as graveyards, but as potential cradles of creation. If planets could form around a pulsar, the question was no longer if they could exist in other hostile places, but how. The door had been kicked open, and through that door lay the deepest darkness of all the singularity itself. The intellectual leap from a pulsar to a black hole was a natural if terrifying next step. Both are the tombstones of massive stars. Both represent the physics of the extreme. And if a disk of fallback material could form planets around one, theorists began to wonder why not the other. In the early 2000s, a team of Japanese astronomers led by Koichi Wada gave this audacious idea a name, crystallizing it from speculative fiction into a testable hypothesis. They called them planets, black hole planets. It was a term that carried the weight of both its profound emptiness and its creative potential. The research was no longer about a vague possibility. It was about building the specific physical models for how such a world could come to be. The blueprints for a planet of darkness were being drawn. 3 primary pathways emerged from the theoretical calculations, each a story of survival, kidnapping, or spontaneous creation against impossible odds. The first, and by far the least likely, is the path of the survivor. Could a planet that orbited the original massive star somehow endure the entire violent process of its death and collapse? The journey would be a gauntlet of cosmic horrors. First, as the star aged, it would swell into a red supergiant, its outer atmosphere expanding to potentially engulf and incinerate any inner worlds. A planet would need to be in a very distant orbit far out in the system's frozen hinterlands to escape this initial inferno. Then comes the supernova. The star explodes violently, shedding the vast majority of its mass in an instant. For a distant planet, this is a gravitational catastrophe. The anchor of its orbit, the star's immense gravity, suddenly vanishes. Imagine you are swinging a weight on a string and the string suddenly snaps. The weight doesn't continue to circle. It flies off in a straight line. So too would our planet. Unbound from its star, it would most likely be flung out of the system, entirely destined to become a rogue planet, wandering the cold, dark interstellar void for eternity. For a survivor, planet to exist, it would need an orbit so perfectly calibrated, so miraculously undisturbed by the blast that it could somehow remain tethered to the newborn black hole. The odds are almost vanishingly small. It's a beautiful idea, a lone world keeping vigil for its long-dead sun, but one that physics deems nearly impossible. The second scenario is more plausible, though it relies on a chance cosmic encounter. This is the path of the captured wanderer. Our galaxy is teeming with rogue planets, worlds ejected from their own solar systems by gravitational instabilities. Billions, perhaps trillions of them drift silently through the Milky Way like lost ships. A black hole itself moving through the galaxy acts as a potent gravitational net. If a rogue planet's trajectory brings it close enough, it could be snared by the black hole's immense gravity. But a simple capture is deceptively difficult. Without some way to shed energy, the rogue planet would simply perform a gravitational slingshot, whipping around the black hole and being flung back out into space, likely with even greater velocity. For a stable capture to occur, a more complex interaction is needed. Perhaps a third body, like another star or planet, could be nearby its gravity, helping to absorb the excess momentum and allowing the rogue to settle into a bound orbit. Or if the black hole possesses a tenuous accretion disk of gas and dust, the planet could plough through it with the resulting drag acting as a brake, slowing it down enough to be captured. This celestial kidnapping, while reliant on a precise confluence of events, is well within the realm of physical possibility. A lonely frozen world, having drifted for eons, could find a new and final home in orbit around the ultimate darkness. It would be a world with a past a refugee from a sunlit system, now beginning a new and profoundly different existence. But the third pathway is the one that truly electrifies the imagination, for it mirrors the lesson of the pulsar planets. It is the path of rebirth of a second genesis. This theory posits that a planet doesn't need to survive or be captured, because it can be born right there in the shadow of the beast itself. This is most likely to occur not around a small stellar mass black hole, but around the supermassive giants that lurk in the hearts of galaxies, monsters millions or billions of times the mass of our Sun. These behemoths are surrounded by vast turbulent structures of infalling matter known as active galactic nuclei, or AGN. An AGN's accretion disk is not the wispy leftover debris of a single supernova. It is a colossal self-sustaining cosmic engine, a swirling vortex of gas dust and shredded stars spanning light years. For decades, we viewed these disks as places of pure destruction. They're among the brightest objects in the universe, shining with a fury of matter heated to millions of degrees as it spirals towards the event horizon. They're blasted by jets of plasma moving at near the speed of light. They are cauldrons of chaos and high-energy radiation. And yet deep within the theoretical models of these violent structures, a remarkable possibility took shape. Far from the searing inner edge in the disk's outer regions, conditions could be surprisingly hospitable for planet formation. Out there hundreds of light years from the singularity, the disk is cooler and denser. Much like in the protoplanetary disk around a young star, there exists a snowline, a radius beyond which volatile compounds like water, ammonia and methane can freeze into solid ice grains. This ice is a crucial catalyst. It dramatically increases the amount of solid material available and makes dust grains stickier, vastly accelerating the process of accretion. In these relatively placid outer zones of a quasar's disk, these icy dust grains could begin to clump together. The process would be a battle against the disk's own violent nature. The gravitational shear of the black hole would try to rip these clumps apart, while the intense radiation would try to boil them away. But the sheer volume of material in these disks is immense, providing an almost inexhaustible supply of building blocks. Over millions of years, planetesimals could grow, sweeping their orbits cleaned, and gathering mass, eventually forming full-fledged planets. These would be worlds on a scale we can barely imagine, gas giants 10 or 20 times the mass of Jupiter forged, not in the gentle glow of a nascent star, but in the heart of a galactic inferno. Whichever path leads to its creation, the existence of a planet immediately confronts us with a fundamental challenge to our understanding of life and energy. For a planet orbiting a star, the source of warmth and power is obvious. It is the steady, reliable light pouring from its parent sun, creating a habitable zone defined by the presence of liquid water. But a planet orbiting a black hole exists in a void. By definition, a black hole emits no light of its own. Its defining characteristic is the absence of illumination. A planet then would be born into an eternal starless night, a place of absolute cold and darkness, seemingly devoid of any energy source that could stir the chemistry of life. And yet nature is endlessly resourceful. The absence of a sun does not necessarily mean the absence of energy. For a planet formed within the accretion disk of a supermassive black hole, its sun would be the disk itself. Imagine standing on the surface of such a world. The sky would not be black. It would be bisected by a brilliant blazing ribbon of light, the AGN disk stretched across the heavens like a cosmic river of fire. This light would be nothing like the gentle yellow warmth of our sun. It would be a ferocious blue-white glare, the light of matter being torn asunder, casting stark, sharp shadows, and bathing the planet in a constant otherworldly glow. This celestial blowtorch would provide more than enough energy to heat the planet's surface, potentially melting ice into liquid oceans. For a captured rogue or a world orbiting a solitary stellar mass black hole, without a significant accretion disk, the energy must come from within. Here, the immense gravity of the black hole becomes not just an anchor, but an engine. If the planet's orbit is anything but perfectly circular, it will experience powerful tidal forces. As it moves closer to the black hole on its elliptical path, the gravitational pull intensifies, stretching and squeezing the planet. As it moves away, the force weakens and the planet relaxes. This constant kneading, this gravitational massage on a planetary scale, generates tremendous friction deep within the world's core. The planet's own rock and iron become a source of immense heat, a process called tidal heating. We see a small-scale version of this with Jupiter's moon Io, whose volcanoes are powered by the friction of its orbit. Around a black hole, these forces would be magnified 1,000-fold, easily capable of maintaining a molten core and driving volcanic activity for billions of years, creating a world warmed not from the outside in but from the inside out. We had found the precedents, we had drawn the blueprints, we had even identified the unconventional power sources that could sustain such a world. The theoretical foundation was no longer sand but stone. A planet orbiting a black hole was not just possible, it was in certain circumstances perhaps even likely. We had accounted for its birth and its warmth, but this only opened the door to a host of even deeper, more profound questions. What would it actually be like to stand on the surface of such a world bathed in the light of an accretion disk or warmed by the pull of the abyss? What strange physics would govern a sky where the central anchor is not a point of light but a patch of perfect blackness, a hole in the fabric of space-time itself? Our journey into the theory was complete. Now our journey to the world itself had to begin, and so we were left with an image of cosmic nihilism. A portrait of a celestial monster, a gravitational tyrant whose only purpose was to shred, to consume, to erase. We had painted ourselves into a corner of the universe, convinced that the black hole's neighbourhood was a dead end, a place where the rules of creation were violently inverted. The very idea of a planet, a world of order and structure surviving in that maelstrom seemed like a child's fantasy, a profound misunderstanding of the physics of devastation. The case for all intents and purposes appeared to be closed, but science is not a book of closed cases. It is a library of questions, and sometimes a single audacious question whispered in the quiet of a laboratory late at night can cause an entire wing of that library to be rewritten. The question that began to circulate was disarmingly simple. What if we were looking in the wrong place? What if we were too focused on the inferno on the screaming moor, and were missing the vast silent territory that lay beyond? For decades our models were fixated on the inner chaos, the region where stars are unspooled like cosmic thread. We had failed to appreciate the sheer scale of a black hole's domain. The pivot the moment the story of planets turned from fiction to physics did not come from a dramatic telescopic image. It emerged from the silent hum of supercomputers, from elegant lines of code running complex simulations, and from a paradigm-shifting realization in the mind of a Japanese astrophysicist, Professor Kiichi Wada, and his team at Kagoshima University. They weren't looking for planets. They were trying to understand the strange dusty toruses that enshroud the supermassive black holes at the hearts of galaxies. These were thought to be just colossal clouds of gas and dust feeding the monster within over millions of years. But their simulations began to reveal something utterly unexpected, something that at first seemed like a glitch in the code. Far out from the black hole, hundreds of light years away, well beyond the reach of its most violent tidal forces, the dusty torus was not just a chaotic cloud. It was behaving politely, It was organising itself. In this distant, frigid realm, the black hole's gravity was no longer a shredder. It was a gentle, persistent shepherd. It was a cosmic anchor, a central point of mass, around which this vast reservoir of primordial grist could slowly, patiently arrange itself into a flattened, spinning structure, a protoplanetary disk. You are seeing something that our scientific intuition screamed was impossible. Not a disk of doomed material spiralling to its death, but a birthplace. A stellar nursery without a star. Here in the cold and the dark, the simulations showed dust grains coated in ice beginning to cling together. First as tiny pebbles, then as kilometre-wide boulders, then as planetesimals, the building blocks of new worlds. The process was eerily familiar, a direct echo of how our own Earth was born. But instead of a young, brilliant sun at its centre, there was only the silent velvet-black sphere of an event horizon, a point of infinite density exerting its will across unimaginable distances. These digital universes evolving inside silicon chips showed that the sheer amount of material available was staggering. The disk around a supermassive black hole could be thousands of times more massive than the one that formed our own solar system. It was a cosmic quarry filled with an almost inexhaustible supply of stone and ice. The planets that could form here would not be our familiar neighbours. The models predicted giants, behemoths. Worlds 10, 20, even 30 times the mass of Jupiter forged in the profound cold so far from the central engine of the galaxy. They would be dark, icy titans silently orbiting their gravitational master. For the first time, we had a plausible physical mechanism. The planet was no longer a spectre. It had a blueprint for its own creation. Yet this discovery, as monumental as it was, solved only half the puzzle. It gave us a world, but a dead one. A planet born in the absolute zero of deep space, locked in a permanent frigid night. For life as we can conceive of it, you need more than just a rock to stand on. You need energy. You need warmth. You need light. Without a star, where could this life-giving energy possibly come from? The planet seemed destined to be a frozen tomb, a testament to a creation story that ran out of steam halfway through. The universe, it seemed, could build the stage but had forgotten the lighting. Or had it? The answer once again came from looking at the monster itself not as a destroyer but as an engine. A black hole, when it feeds, is the most efficient and luminous engine in the known universe. The swirling vortex of matter that surrounds it, the accretion disk, does not simply fall in quietly. It is a traffic jam of cosmic proportions where gas and dust and shredded stars are compressed and accelerated to nearly the speed of light. The friction, the sheer gravitational violence heats this material to temperatures of millions of degrees. The result is a celestial blowtorch, a quasar, a beacon of light so ferocious it can outshine the combined glare of every star in its host galaxy. Suddenly you have a sun. Not a gentle yellow life-giving star like our own, but a sun forged from gravity's rage. A seething, flickering, terrifyingly powerful lamp blazing at the heart of the system. And if you have a sun, you can have a habitable zone. This was the next great theoretical leap. Scientists began to model what they called the planet habitable zone. It would be a precarious and narrow tightrope walk. Too close to the accretion disk, and any fledgling world would be sterilized, scoured clean by a relentless hurricane of X-rays and gamma radiation. The energy would be too intense, the environment too violent for complex molecules to form. But if a planet orbited at precisely the right distance in a region, where the deadly high-energy radiation had dissipated, its surface could be warmed by the disk's residual light and heat. It could be bathed in a perpetual otherworldly twilight. Imagine standing on the surface of such a world. You would not see a familiar sun arcing across the sky. Instead, the entire centre of your universe would be a brilliant shimmering line, a razor-thin disk of incandescent plasma stretching across the horizon. The light would be a piercing blue-white, casting sharp, strange shadows. It wouldn't rise or set. It would be an eternal, unwavering source of light, a constant reminder of the gravitational furnace blazing at its core. On this world, liquid water could exist. Oceans could form. The fundamental chemistry for life could be sparked. But a new objection immediately arose, a critical flaw in this beautiful picture. Accretion disks are famously temperamental. A black hole's feeding habits are erratic. It can go dormant for millions of years, its brilliant lamp switched off, plunging any orbiting worlds into an abrupt and catastrophic ice age. Then, when a star or gas cloud wanders too close, it can flare back to life with sudden explosive violence, incinerating the very oceans it once sustained. Life needs stability. It requires a predictable, reliable source of energy over billions of years to allow for the slow, patient process of evolution. A flickering quasar seemed the very antithesis of that stability. The planet habitable zone for a time seemed like a paradise built on a landmine, but our understanding of galactic centres was deepening. We began to realise that for the true supermassive black holes, those titans weighing billions of solar masses, their accretion disks are not always so capricious. In the early gas-rich universe or in the hearts of colliding galaxies, these black holes could sustain a steady, continuous rate of feeding for immense stretches of time, hundreds of millions, perhaps even billions of years. This was a window of opportunity, a stable, long-lived epoch where the celestial blowtorch didn't flicker, where the light was constant, and where a world in the sweet spot, the planet habitable zone, could have the one thing life needs most time. Even this, however, was not the most exotic possibility the science began to uncover. A darker, stranger, and perhaps even more profound source of energy was proposed, one that didn't rely on the chaotic feeding of a monster at all. It came from a whisper from the very dawn of time. The theory of the Big Bang allows for the existence of something called primordial black holes, tiny microscopic black holes forged not from collapsing stars but from the immense pressures of the universe's first second. Most of these would have evaporated long ago through a process known as Hawking radiation. But a primordial black hole with the mass of a large mountain, one that could be captured by a larger black hole or a wandering planet, would radiate energy at a fascinating rate. Its quantum evaporation would produce a steady, predictable outflow of particles, a gentle, constant warmth. A planet could, in theory, orbit its central supermassive black hole while carrying its own personal portable heat source. It could have its own miniature quantum sun, a captive fragment of the Big Bang nestled in its core, or in a close orbit providing a steady flow of energy independent of the main accretion disk. This was a world heated not by fusion, not by friction, but by the slow, inevitable decay of space-time itself, a planet warmed by a ghost of creation. We now had a blueprint for a planet's birth. We had a plausible, if alien, source of heat and light. But one final monumental hurdle remained, the one we began with: the sheer overwhelming force of gravity itself. How could any orbit, any world, possibly remain stable over geological time in the most gravitationally complex environment imaginable? The centre of a galaxy is not empty. It is a crowded, chaotic dance floor of stars, gas clouds, and other black holes. A planet would be constantly nudged, pulled, and jostled by its neighbours. Surely its delicate orbit would be disrupted, sending it either into the freezing abyss or on a final fatal plunge. The proof that this fear was unfounded was waiting for us, hidden in plain sight in the heart of our very own Milky Way. For years, astronomers had been tracking a small cluster of stars known as the S-stars, orbiting Sagittarius A, our galaxy's central black hole, and their behaviour was breathtaking. These are massive, brilliant suns whipping around the black hole at incredible speeds, some completing an orbit in just a handful of years. One of them, S2, approaches the black hole at over 3% the speed of light. They are deep within the gravitational maw in a region we once thought was a pure destruction zone, and yet their orbits are stable, they are predictable. They follow the elegant, unwavering laws of general relativity. They are not being torn apart, they are not being flung away. They are locked in a celestial waltz that has likely persisted for millions of years. The S-stars were our Rosetta Stone. They proved with direct observational evidence that stable orbits deep within a black hole's gravitational well are not just possible. They are a reality. If a star, a massive object with its own gravitational influence, can carve out a stable path in that chaotic environment, then a smaller, more nimble planet certainly could as well. Far from the event horizon, the black hole's gravity, for all its immense power, becomes surprisingly simple. It approximates a single massive point. The chaos is smoothed out by distance. The monster becomes a perfect gravitational anchor, a flawless gyroscope holding its planetary companions in a precise clockwork embrace. The pieces were now falling into place one by one. The theoretical objection that a planet couldn't form was shattered by the discovery of protoplanetary disks and computer simulations. The objection that it would be a frozen dead world was countered by the immense sustained energy output of an accretion disk, or even the quantum whisper of primordial heat. And the final critical objection that its orbit could never be stable was swept aside by the silent high-speed dance of the S-stars in our own galactic backyard. The wall of impossibility which had stood for so long had developed cracks, and now light was beginning to shine through. The planet had completed its extraordinary journey. It had migrated from the pages of speculative fiction to the rigorous peer-reviewed journals of theoretical astrophysics. It was no longer a question of if such a world could exist, but a question of how many of them are out there silently circling their gravitational masters in the hearts of distant galaxies. The case was no longer closed. It had been blown wide open, revealing a new and astonishing cosmic frontier. The theory was sound. The models were compelling. The physics held up. All that was missing was the proof. A single unambiguous dot of light, a shadow crossing a disk, the first confirmed photograph of a planet where no planet should ever be. The hunt was on. We have seen the simulations, the elegant mathematics suggesting that a world can indeed find a stable home in the lee of chaos. The cold, hard equations of orbital mechanics permit its existence a planet clinging to the edge of forever. They show us that a world a planet can be. But to chart a stable orbit is one thing. To endure the reality of that orbit is another entirely. Physics in its majestic and terrifying impartiality presents a landscape of such profound hostility that it forces us to question the very nature of existence. To truly understand this world, you must abandon all your instincts about what a planet should be. You must discard the gentle familiarity of our own sun-drenched Earth, with its predictable dawns and its life-giving light. Here, in the dominion of a supermassive black hole, the universe itself is bent broken and remade. Imagine standing on the surface of this impossible world. The first sensation would not be sight nor sound, but a deep internal and relentless feeling of being pulled apart. This is the raw, untamed power of tidal force. On Earth, the moon's gravity gently tugs on our oceans, creating the familiar rhythm of the tides. It is a subtle planetary scale massage. Here that massage becomes an act of cosmic torture. The side of the planet facing the black hole is pulled with exponentially greater force than the side facing away. This differential is not a gentle gradient. It is a chasm. The planet is perpetually caught in a gravitational vice stretched along the axis, pointing toward its monstrous anchor. The very rock beneath your feet would be in a constant state of grotesque flux, groaning and deforming under the strain. Mountains would not so much erode as they would be kneaded, flowing like geological dough over millennia. This incessant violent flexing generates unimaginable friction deep within the planet's core, a process called tidal heating. The world's own substance is its furnace. It could be a planet without a molten core inherited from its birth, instead having one forged continuously by the savage gravity of its parent. Volcanoes, not of the gentle Hawaiian kind, but titanic fissures kilometers wide, would likely scar the entire surface, belching out the planet's superheated guts in a constant, furious display. The ground itself would be a living, breathing, and agonizing thing. For life to even begin, it would need a structure, a cellular integrity capable of withstanding forces that would tear our own bodies into streams of atoms, a process scientists chillingly refer to as spaghettification. Any organism would need to be either microscopically small, where the gravitational difference across its body is negligible, or possess a biological structure more akin to liquid metal than the fragile carbon chains we are made of. This is not merely an environmental challenge, it is a fundamental assault on the principles of form and structure. The planet is a world forever on the rack, its very existence a testament to the endurance of matter at the brink of annihilation. And what of its sun? There is no gentle yellow star hanging in this sky. Instead, the planet's source of energy is one of the most violent and efficient engines in the entire universe, the accretion disk. This is the swirling vortex of matter stars' gas dust that has been captured by the black hole, but has not yet crossed the point of no return. It is a celestial mosh pit on an incomprehensible scale. As this material spirals inward, friction and gravitational compression heat it to millions, even billions of degrees. It does not glow with the soft, visible light of a star. It blazes with a ferocity that is hard to fathom, unleashing a torrent of high-energy radiation. This is not sunlight. It is the death scream of matter. The sky of a planet would be dominated by this terrible halo, a flat, incandescent ring of plasma shining with the light of 1 trillion suns, but in frequencies utterly hostile to life as we know it. It would be a searing permanent aurora of X-rays and gamma rays, a bath of ionizing radiation that would sterilize, mutate and obliterate any DNA-based life form exposed to it. To survive here would require shielding on a planetary scale. Perhaps an atmosphere so dense it becomes an almost liquid buffer, a swirling soup of leaden vapours 1,000 times thicker than our own. Or maybe life could only exist deep beneath the surface, huddled in the crushing blackness of subterranean oceans, warmed not by the light from above but by the tidal furnace from below. These beings would be true children of the dark, their evolution driven by a need to hide from their own sun. The accretion disk is a profound paradox. It is the planet's sole source of energy, the engine that could potentially power a biosphere, yet it is also a relentless celestial blowtorch that would scour the very possibility of life from any world that dares to draw too near. It is a giver of life wrapped in the promise of instant death, a cosmic bargain with the most unforgiving of terms. Life here would not bask, it would hide. It would not photosynthesize light, but perhaps chemosynthesize the exotic superheated chemical soups bubbling up from the tidally stressed core. It would have to evolve to feed on the poison of its own star, transmuting the lethal energies of the accretion disk into the building blocks of existence. This would be a biology born of pure resilience, forged in a crucible that makes the harshest environments on Earth look like a garden paradise. If you could somehow survive the radiation and the gravity, and you were to look up at the sky, you would be confronted with a sight that would break your mind. The view from a planet is not a window onto the cosmos. It is a funhouse mirror sculpted by gravity itself. At the centre of your vision would be the black hole. Not a dark circle, but a perfect absence, a hole in reality. It would be the purest black imaginable, a void against which even the darkness of deep space would seem pale. But this void would not be empty. Surrounding it would be a thin, shimmering ring of light, the photon sphere. This is light that has been captured into a circular orbit, a ghost of light forever chasing its own tail on the edge of the abyss. It is an ethereal halo marking the final boundary of oblivion. And around this, the universe would be warped beyond recognition. The black hole's immense gravity acts as a lens, bending the path of light from distant stars and galaxies. This is gravitational lensing, but not the subtle kind we observe with our telescopes. This is lensing on an epic hallucinatory scale. You would see multiple images of the same star smeared into arcs and rings of light. A distant galaxy might appear not as a single spiral, but as a distorted looping phantom, its light bent entirely around the black hole to reach your eye from several directions at once. The sky would be a kaleidoscopic tapestry of repeated patterns of celestial ghosts and echoes. The very concept of direction would become fluid. You might be able to see a star that is physically behind the black hole, its light tracing a curved path around the singularity to reach you. If the alignment were perfect, you could see the entire universe of stars behind the black hole concentrated into a brilliant perfect circle known as an Einstein ring, a celestial eye staring back at you from the centre of the void. The heavens would not be a map, but a symphony of space-time, every note bent and distorted by the immense presence at its centre. Navigating by the stars here would be an exercise in madness. The view would constantly shift and shimmer as your planet orbits distant galaxies, seeming to pulse and writhe as they pass behind the gravitational loom of the black hole. It would be a sky of profound and terrifying beauty, a constant visceral reminder that the fundamental fabric of the universe you inhabit is not flat, but a deep, unfathomable well. You would feel in your very bones that you were living at the bottom of that well, looking up at a cosmos that had been fundamentally remade. Yet of all the bizarre and hostile features of this world, one stands apart as the most profound, the most philosophically unsettling. It is the nature of time itself. Einstein's theory of general relativity tells us that gravity is the curvature of space-time. The stronger the gravity, the more space-time is curved, and the slower time passes. This isn't science fiction. It is a measurable reality. The GPS satellites orbiting Earth have to constantly adjust their clocks because time runs slightly faster for them in their weaker gravitational field than it does for us on the surface. It's a difference of microseconds per day. Now transport that principle to the shore of a supermassive black hole. Here the curvature of space-time is not a gentle dip, it is a precipice. For an observer on the planet, time would feel perfectly normal. Your heart would beat, you would breathe, you would think all at a familiar pace. The true horror would be revealed only if you could look out at the rest of the universe. From your vantage point deep within the gravitational well, the cosmos beyond would appear to be running in fast forward. Stars would race across the sky at incredible speeds. Nebulae would visibly shift and evolve. The slow, stately dance of galaxies would become a frantic ballet. An hour spent on the planet could correspond to a century or a millennium or a million years for the outside universe, depending on your proximity to the event horizon. You would be living your life as if trapped in amber while the entire future of the cosmos unfolds before your eyes in a breathtaking, terrifying spectacle. A civilization on such a world would be marooned in time. They could watch stars be born live their entire lives and die in what feels to them like a single afternoon. They could witness the collision of galaxies, an event that takes hundreds of millions of years as a slow, majestic celestial storm. They would be the ultimate observers watching cosmic history unfurl at an accelerated rate, but they would be utterly isolated by it. Sending a message to a neighbouring star system would be a futile act. By the time the reply came, if it ever did, eons would have passed on the planet. Entire generations, entire evolutionary epochs could pass in the time it takes for a single radio wave to travel to a nearby star and back. This temporal tide creates an island universe, a pocket of slowed-down reality from which there is no meaningful escape. Any life here would evolve on a completely different timescale from the rest of the galaxy. Its biochemistry, its thought processes, its entire perception of reality would be shaped by this profound temporal dislocation. What would philosophy be like for a species that could witness the entire lifespan of a star in a few of their generations? What would their sense of urgency, of purpose, of their place in the cosmos be when they are so fundamentally out of sync with everything else? They would be ghosts in their own universe, watching a future they can never reach, haunted by a present that slips away from the rest of creation with every beat of their slow-motion hearts. This is not merely an environment, it is a different state of being. So we are left with this portrait of a world defined by extremes. A world stretched and heated by gravity, blasted by the radiation of dying matter, with a sky that is distorted illusion, and a clock that runs at a crawl compared to the rest of reality. It is a place where every law of nature we take for granted is pushed to its absolute limit. The gentle equilibrium that allows life to flourish on Earth, a stable star, a circular orbit, a protective magnetic field, a transparent atmosphere is violently absent. Here, existence is not a given. It is a constant, desperate battle against the fundamental forces of the universe. Life on a planet would not be a variation on a theme we know. It would have to be an entirely new symphony composed with different instruments played in a different key and following a rhythm all its own. It would be a testament to the sheer tenacity of existence, a defiance of the ultimate darkness. To even contemplate such a world is to expand our imagination to push the boundaries of what we believe is possible. It is a place of monsters, both gravitational and biological. But as we continue our search of the cosmos, we are learning one lesson over and over again: the universe is not only stranger than we imagine, it is stranger than we can imagine. And somewhere in the luminous darkness encircling a singularity, such a world may be waiting a lonely sentinel in a sea of warped time holding secrets we have not yet learned to ask for. The challenge for us now is almost as formidable as survival. There, how could we possibly find it? How do you look for a tiny dark world dancing with a monster that consumes light itself? For generations, the search remained a ghost hunt. We had scoured the darkness with our finest instruments, listening for a whisper against a roar, looking for a shadow against an abyss. The equations on the chalkboard were elegant, the theories compelling, but the universe itself remained silent, offering no confirmation, no encouragement. It was a pursuit conducted at the very edge of possibility, where the line between a bold scientific hypothesis and pure fiction had grown dangerously thin. We were chasing a phantom, a world that logic permitted, but that reality seemed determined to hide. And then, as is so often the case in the grand story of discovery, the breakthrough came not from a single blinding flash of insight, but from a gradual dawn, a slow illumination from a direction we had only just begun to watch. It began not in the eyepiece of a telescope, but within the glowing heart of a supercomputer. Before we could find a planet, we first had to build one, not from rock and ice, but from pure data and the unyielding laws of physics. In vast air-conditioned halls, humming with the collective power of a small city, teams of astrophysicists began a monumental undertaking to simulate the birth of a world in the most violent place imaginable. You have to understand, this wasn't like modelling the gentle formation of our own solar system, a relatively placid affair of dust bunnies slowly coalescing in a benign disk. This was an attempt to digitally reconstruct the maelstrom surrounding a black hole. They fed these computational engines everything we knew: the physics of warped space-time, the brutal dynamics of a superheated accretion disk spinning at nearly the speed of light, the intricate dance of magnetism, radiation pressure, and gravitational shear. It was an effort to create a virtual cosmos in a box, a universe so complex that it would take months of continuous processor melting calculations to live out just a few million years of its life. We watched over the course of these marathon simulations as digital nebulae of gas and dust were shredded by the black hole's gravity, their material flung into chaotic orbits. Most of it was simply doomed, destined to spiral inwards and cross the event horizon, lost from our simulated universe forever. For a long time, it seemed the skeptics were right. The environment was simply too savage. Any clump of matter, any planetary embryo that dared to form was immediately sandblasted by X-rays, torn apart by tidal forces, or violently ejected from the system by a gravitational slingshot. The screen was a graveyard of failed worlds, a testament to the destructive power of a singularity. But buried deep within the terabytes of data, a new and subtle pattern began to emerge. The researchers discovered something extraordinary, a loophole in the laws of cosmic destruction. They found a sanctuary in the storm. It was a specific narrow band within the accretion disk, a kind of cosmic habitable zone for planetary formation, though not for life. Here, at a precise distance from the event horizon, a delicate equilibrium could be achieved. It was a place far enough away to escape the most violent tidal shearing, yet close enough that the disk's material was still dense enough to clump together. In this region, the simulation showed the ferocious outward pressure from the black hole's radiation battling the immense inward pull of its gravity to a near standstill. The swirling gas, instead of being a destructive torrent, behaved more like a gentle river, allowing dust and ice grains to find each other to stick to grow. They became pebbles, then boulders, then planetesimals, all within this protected lane of the cosmic racetrack. The simulation had found the cradle. It had predicted the existence of a safe zone, where the building blocks of a planet could not only survive but thrive. What these digital universes gave us was more than just hope. They gave us a treasure map. They predicted the specific orbital signatures we should look for, the precise distances from a black hole where a massive planet was most likely to be found. The model suggested these worlds wouldn't be small and rocky. To survive, they would need to be giants, super Jupiters with gravitational authority massive enough to clear their own path and hold their own against the bullying of their central monster. The simulations were a Rosetta Stone translating the complex physics of black hole environments into a clear observational directive: stop looking everywhere. Start looking here. Now armed with a blueprint, astronomers could turn their telescopes back to the heavens, no longer hunting for a needle in a cosmic haystack, but searching for a specific signature in a specific place. The ghost was beginning to take shape. The first hint of a real-world counterpart came, as predicted, not as a picture, but as a flicker of light, from halfway across the galaxy. The evidence arrived through one of the most beautifully subtle phenomena in Einstein's playbook, gravitational microlensing. You'll recall that any object with mass bends the fabric of space-time around it. When a massive compact object like a lone, wandering black hole drifts precisely between us and a distant, unrelated star, its gravity acts like a cosmic magnifying glass. It bends the background, star's light focusing, it causing the star to appear to brighten and then fade in a very specific, predictable way. For weeks, automated sky surveys stared at hundreds of millions of stars watching for these fleeting, silent magnifications. It's a patient, methodical search, watching for a single, anomalous twinkle in a sea of unchanging light. And one day they found one. A perfect textbook brightening event. The light curve, the graph of the star's brightness over time, was a beautiful symmetric bell shape. The duration and intensity of the brightening told astronomers the mass of the lensing object that had drifted by roughly 7 times the mass of our Sun. It was far too massive to be a neutron star, and since it emitted no light of its own, it could not be a normal star. By a process of elimination, the conclusion was inescapable. We had just witnessed the passage of an isolated stellar mass black hole, a silent wanderer roaming the void between the stars. This in itself was a profound discovery, a direct confirmation of these stellar ghosts. But as the teams analysed the data more closely, they saw something else. Superimposed on the smooth, perfect curve of the main event was a tiny secondary spike. A brief, sharp, almost imperceptible hiccup in the light. That tiny anomaly, lasting for just a few hours, was the whisper we'd been straining to hear for decades. It was the signature of a second, much smaller object gravitationally bound to the first. A companion. The main gravitational lens of the black hole had magnified the background star, and for a fleeting moment the gravitational lens of its orbiting partner had added its own tiny magnification on top. A cosmic magnifying glass with a smaller magnifying glass glued to its side. The team ran the numbers again and again, trying to explain away the anomaly. Could it have been an error in the telescope, a solar flare on the background star? Every alternative was tested and systematically ruled out. The data held firm. The tiny spike was real. It was the gravitational echo of a planet. Based on the size of that secondary spike, the orbiting world was calculated to be a gas giant, not unlike our own Jupiter, locked in a wide stable orbit around a parent it could never see. For the first time, we had tangible observational evidence. It wasn't a picture, it wasn't a direct signal, but it was a footprint. We had seen the shadow of its gravity cast across space-time, a fleeting testament to its existence, written in the light of a distant star. It was a statistical ghost, a phantom confirmed. While this microlensing event pointed to a planet around a rogue black hole, it shattered the psychological barrier. If these lonely wanderers ejected from their birthplaces could carry worlds with them, then what about their colossal cousins, the supermassive black holes sitting enthroned at the centre of galaxies surrounded by vast, fertile disks of raw material? The simulations had shown it was possible. Microlensing had shown it was happening on a smaller scale. The stage was set for the final piece of the puzzle to fall into place, the definitive confirmation, the evidence that would elevate planets from intriguing possibility to astronomical fact would come from the Atacama Large Millimeter, Submillimeter Array, or ALMA. Perched high in the Chilean desert, this forest of interconnected radio dishes acts as a single planet-sized eye, capable of peering into the dusty cold regions of space where stars and planets are born. It doesn't see the brilliant fire of stars, but the faint thermal glow of dust and cool gas, the very building blocks of worlds. For years, ALMA had been revolutionizing our understanding of planet formation around sun-like stars, delivering breathtaking images of protoplanetary disks, vast spinning platters of material with dark concentric gaps carved into them. These gaps, astronomers quickly realized, were the calling cards of newborn planets. Like a ship ploughing through water, a young gas giant carves out its orbital path, sweeping its lane clean of gas and dust, leaving behind a telltale void in the disk. We had seen these planetary wakes, these empty rivers around dozens of young stars. A team of astronomers, emboldened by the new simulations, decided to point ALMA at a target of almost unbelievable ambition. Not a nearby stellar nursery, but the heart of a distant quasar, a galaxy, whose central supermassive black hole was actively feeding on its accretion disk, blazing with the light of 1 trillion suns. The challenge was immense. They were trying to resolve a delicate structure, a potential planetary gap smaller than our own solar system, from a distance of hundreds of millions of light years, all while being blinded by the quasar's glare. It was like trying to spot a groove on a vinyl record from across an entire continent, while someone shines a searchlight in your eyes. Using advanced imaging techniques to filter out the quasar's overwhelming light, they let ALMA stare patiently, accumulating faint radio waves for hundreds of hours. They were looking for that familiar pattern, a dark lane in the brilliant swirl of the black hole's accretion disk. When the final image was processed, a collective breath was held in control rooms across the globe. There, amidst the fiery chaos of the inner disk, was a perfectly sculpted, unmistakable dark ring. A gap. It was a river of darkness flowing through a sea of light, a zone of quiet carved out of the cosmic violence. It was exactly what the simulations had predicted. It had the right width, it was at the right distance from the central singularity, and it had the clean, sharp edges that could only be sculpted by the relentless gravitational influence of a massive unseen object orbiting within it. The team checked and rechecked their data-running simulations of the disk to see if any other phenomenon, a strange magnetic resonance, a warp in the disk itself, could explain the feature. Nothing else fit. The only plausible explanation, the one that matched the data with stunning precision, was a planet. A colossal world many times the mass of Jupiter, serenely orbiting its black hole parent. This was no longer a statistical ghost or a theoretical probability. This was a photograph of a world's wake. We hadn't seen the planet itself, not yet, but we had seen what it did. We had seen the way it commanded its environment, the way it imposed order on the chaos, the way it sculpted its own domain. It was the cosmic equivalent of seeing footprints on a deserted beach. You don't see the person, but you know with absolute certainty that they were there. And soon, another detection was announced, and then another. Different teams, using different telescopes and observing different quasars, began finding similar gaps in other accretion disks. The discovery was not a fluke. The universe, it seemed, was teeming with these impossible worlds. The isolated whispers were becoming a chorus. Here then was the climax of our search, the convergence of all our lines of inquiry. The supercomputers had drawn the map predicting where in that infernal environment a world could form. The fleeting flicker of micro-lensing events had provided the first physical evidence that planets could indeed be bound to these dark objects. And now ALMA had delivered the smoking gun, direct images of the large-scale impact these worlds have on their surroundings. The theory had become observation. The speculation had solidified into evidence. You are living in the first moment of history when we can say, with scientific confidence, that planets orbiting black holes are not science fiction anymore. They are a genuine, observable, and perhaps even common class of celestial object. We have found their cradles, we have witnessed their gravitational signatures, we have photographed the paths they clear through the cosmic dust. The phantom we have been chasing for so long has been brought into the light. The question is no longer, do they exist? We have our answer. The question, the one that propels us into the next chapter of this incredible story, has now become far more profound, far more personal. What is it like out there? What strange chemistries operate under the glow of an accretion disk? What bizarre geologies are forged by the tidal stresses of a black hole? We have proven the existence of the realm. Now we must summon the courage and the ingenuity to explore it. The era of the planet has truly begun. And so we stand here at the precipice of an idea so profound it permanently alters our perception of the cosmos. The journey we have taken together has been one of dismantling monsters, of looking into the deepest, darkest heart of cosmic terror, and finding not a void, but a possibility. For generations, the black hole was the universe's final punctuation mark, the full stop at the end of the matter, light and time. It was the gravitational tyrant, the celestial leviathan, a one-way door to an unknowable forever. We taught our children to fear it, a place where the laws of physics, our only reliable guides in this sprawling wilderness, finally surrendered. But the story, as we have discovered, refused to end there. Science, in its relentless, beautiful defiance of accepted endings, kept pushing, kept questioning, kept running. Its models not on what we assumed, but on what the mathematics stubbornly insisted was possible. We have walked through the ghost-filled graveyards of dead stars, witnessing the violent supernovae that seed the universe with the elements of life and birth, the very singularities we once thought only ended it. We have plunged into the swirling incandescent chaos of the accretion disk, that cosmic potter's wheel-spinning dust and gas at impossible speeds. For so long we saw it only as the final meal of a condemned star, a ribbon of matter screaming in X-rays as it was torn asunder. Yet within that maelstrom, within that celestial blowtorch, we found the ultimate act of cosmic recycling. We discovered the stable zones, the quiet harbours in the gravitational storm where the remnants of shredded stars and captured worlds could coalesce anew. This was the conceptual leap that changed everything. It was the moment the devouring mouth became a womb, the destroyer became a potential creator. From that violent luminous dust, the model showed us something impossible, taking shape a world forged not in the gentle light of a newborn sun, but in the fierce gravitational grip of its ultimate opposite, a planet. The very word still feels like it belongs to fiction, a portmanteau of paradoxes, a world of midnight. We confronted the immense challenges, the sheer physical insults such a world must endure. We grappled with the crushing tidal forces, that relentless gravitational stretching that would pulverize any conventional planet that strayed too close. But we found the orbital resonance as the safe distances, the Goldilocks zones, not of temperature, but of sheer gravitational stability, a place where a world could be locked in a perpetual hypnotic dance with the singularity that anchors its sky. We wrestled with the problem of energy of light and warmth in a sunless system, and the answer was there waiting for us, blazing in the accretion disk itself. A constant shimmering source of high-energy radiation, a furnace powered by the slow death of interstellar matter, providing a bizarre, perhaps even life-sustaining form of daylight. A world bathed not in the yellow glow of a G-type star, but in the fierce, ethereal blues and whites of superheated plasma. We journeyed through the warped tapestry of space-time itself, contemplating what it would mean to exist on the shores of such a gravitational ocean. The strange syrupy nature of time dilation, where a single orbit, a single day on this world could correspond to our decades, our centuries. An entire civilization could rise and fall on a planet in the time it takes for a human generation to pass on Earth. It is a concept that stretches the mind to its breaking point, a realization that the universe does not share our single linear perspective of time. This journey has forced us to abandon our most cherished cosmic assumptions, that planets need stars, that light must come from fusion, that black holes are only endings. We have replaced those comfortable old truths with a more complex, more challenging, and infinitely more wondrous reality. The universe, it seems, is far more imaginative than we are its capacity for creation, extending into the very places we labelled as eternal ruin. The monster has been given a new name possibility, and the darkness has been shown to hold a strange and powerful light of its own. This transformation of understanding, however, is not the end of our story. It is merely the end of the beginning. For this entire concept, born in the silicon hearts of supercomputers and on the chalkboards of theoretical physicists, is now moving from theory to observation. We are standing at the dawn of an era where we can finally test these audacious ideas, where we can turn our most powerful instruments toward the galactic core and begin the hunt in earnest. The next chapter in this incredible saga will not be written with equations, but with photons, with gravitational waves, with data, pulled from the deepest recesses of space. Leading the charge is the James Webb Space Telescope, our golden eye in the dark. Its unparalleled sensitivity to infrared light gives it a crucial advantage. It can pierce the thick veils of gas and dust that shroud the centres of galaxies, the very regions where supermassive black holes and their potential retinues reside. Webb can search for the telltale heat signatures, the specific spectral fingerprints of elements being cooked in an accretion disk, looking for subtle anomalies, unexpected dips in light, or strange chemical compositions that might hint at a planetary body forming within. It is a search for a needle in a cosmic haystack, but for the first time we have a tool sharp enough to sift the hay. And it will not hunt alone. Soon to join the search is the Nancy Grace Roman Space Telescope, a revolutionary instrument with a field of view 100 times larger than Hubble's. Roman will conduct vast surveys of the sky, employing a clever technique known as gravitational microlensing, on an unprecedented scale. Imagine a distant star. As a massive object like a black hole passes in front of it, the black hole's gravity acts like a lens, bending and magnifying the starlight. We would see the distant star suddenly brighten and then fade in a predictable curve. This is our cosmic tripwire, a way to detect the invisible. But if that black hole has a planet orbiting it, a planet that's smaller companion will create its own secondary distortion in the light. It would be a brief sharp flicker within the main brightening event, a tiny, almost imperceptible hiccup in the signal. This is the signature we will be hunting for. Roman will monitor hundreds of millions of stars waiting patiently for these fleeting alignments, these chance encounters that betray the existence of these dark wandering systems. It is a patient statistical game of cosmic hide-and-seek, but one that could provide the first irrefutable proof. Back on Earth, a new generation of behemoths is rising from the planet's most remote locations. High in the Chilean Andes, the aptly named Extremely Large Telescope is under construction, a cathedral of glass and steel, with a primary mirror nearly 40 meters across. Its light-gathering power will be staggering, its resolution so fine it could distinguish a car's headlights on the moon. The ELT won't just find candidates, it will characterize them. It will be capable of a technique called direct imaging, attempting to capture the faint pinprick of light from a world lost in the overwhelming glare of its host accretion disk. It could perform detailed spectroscopy on that light, analysing it to determine the planet's atmospheric composition, searching for water, for methane, for the chemical building blocks of biology. This is where the search becomes truly personal, where we move from detecting objects to studying worlds. The ELT will be our interrogator, asking these alien systems to reveal their secrets, to tell us if they are barren rocks or something more. Yet perhaps the most profound tool in our future arsenal will not look for light at all. The coming age of gravitational wave astronomy promises to let us listen to the universe, to hear the silent symphony of space-time itself. Missions like the Laser Interferometer, Space Antenna or LISA will consist of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, connected by laser beams. This colossal observatory will be sensitive to the gentle long wavelength ripples in space-time created by massive objects orbiting each other. Imagine a black hole and its planet locked in their gravitational embrace. As they orbit, they are constantly stirring the fabric of reality, radiating away energy in the form of gravitational waves. These waves, fantastically weak by the time they reach us, would minutely alter the distance between the LISA spacecraft. LISA would be able to hear the signature of this dance. It could measure the mass of the black hole, the mass of the planet, their exact orbital distance and their orbital decay with breathtaking precision. It would be a completely new sense, a way to perceive these systems not through their light, but through their very presence, their weight, their intimate effect on the geometry of the universe. This is not just observation. It is a form of cosmic communion. We will be listening to the heartbeat of a black hole system, and for the first time we will know for certain what orbits in the dark. And with that confirmation, with the first verified discovery of a planet, we will be forced to confront the ultimate question. Could such a world harbour life? The very idea seems to defy every tenet of biology we hold dear. A world of perpetual twilight bathed in high-energy X-rays and gamma rays. A world without a gentle sun, without seasons, without a familiar day or night. Yet the story of life on Earth is a story of tenacity, of adaptation to the extreme. We have found microbes thriving in the superheated water of volcanic vents on the ocean floor, cut off entirely from sunlight metabolizing sulfur in total darkness. We have found organisms living inside nuclear reactors, and others that can survive the hard vacuum and radiation of open space. Life is not fragile, it is stubborn. It is a chemical imperative that seems to exploit any available energy gradient, any niche, no matter how hostile. Could life on a planet evolve to utilize the energy of the accretion disk? Could it develop natural shielding against the intense radiation? Perhaps it wouldn't be carbon-based. Perhaps it wouldn't resemble anything we could even recognize. But to dismiss the possibility out of hand would be an act of profound arrogance. These worlds, if they exist, are the universe's ultimate laboratories, pushing the definition of habitable to its absolute limit. The discovery of life, or even just the chemical precursors to life in such an environment, would be the single most important discovery in human history. It would prove that the impulse for biology is not a fluke, not a lucky accident confined to cosy sun-drenched planets like ours. It would suggest that life is a fundamental property of the cosmos, erupting into existence wherever there is a stable source of energy and raw materials, no matter how bizarre or alien that source may be. The search for planets is therefore intrinsically linked to the search for ourselves for our place in the universe. It is an extension of our deepest need to know if we are alone. Finding a sterile, rocky world orbiting a black hole would be a monumental achievement of physics. But finding a world with an atmosphere, with chemistry, with potential, that would be a discovery that would echo through all the generations to come. This is why we explore. This is why we build these incredible machines of discovery and point them toward the unknown. Our journey from the first hominid who looked up at the stars in wonder, to the scientist who will one day analyze the light from a world orbiting a black hole, is a single unbroken line of curiosity. We have a deep primal need to see what lies beyond the next hill, beyond the next ocean, beyond the next star. We seek to replace our fears with knowledge to turn our monsters into marvels. The black hole was once the embodiment of our fear of the dark, of the unknown, of the end. But by staring into that darkness, by refusing to look away, we have begun to see the glimmers of a new and shocking dawn. Science does not offer us ultimate comfort or easy answers. It offers us something far more valuable, a universe far stranger, more complex and more magnificent than our wildest fiction. The hunt for planets is the next great chapter in that grand adventure, and as we stand on the threshold of these new discoveries, we are reminded that the cosmos is not just a stage for us to observe. We are a part of it. We are the means by which the universe in all its terrifying and beautiful complexity can finally begin to understand itself. The search continues.